welcome to
this edition of
Math in Your Face, the J Squared Show. Hi, I'm Jane Wortman, head of the math department here at Beverly Hills High School.
And I'm Julia Bloom, the academic director of the Beverly Hills Tutoring Center.
And Julia and I are here today to help you with algebra. Now, we hope you use this program
to help you review things that you learned in class already.
Or possibly to see things that you missed because you were absent from class.
But try not to be absent. But in the meantime, we want all of you at home to work along with us here. And remember,
if you want to learn math at a better pace,
try putting some math
in your face. Okay, Julia, we're here today to work on concepts for algebra from Chapter 7 of our algebra book. And Chapter 7 is going to deal with about 3 or 4 different ideas, the first of which is relationships between two variables. And we are going to look at pictures of those those relationships. To graph a relationship given by an equation in two variables, that's called a linear equation, we actually use a line. And in order to create the line, we need to find some points to plot that are on the line. And their relationship to the equation is that they must solve the equation. And most of these lines come from actual situations. So let's look at our first situation. We've got a connection between time of day and temperature. Now, this might be a little cold for Los Angeles, but what happens if when we got up in the morning, it was negative 11 degrees, and then the temperature continued to rise as the day went on every hour?
Okay, so here TT is temperature. So our temperature is negative 11, and then it keeps going up to H. All right, H is measured in hours. All right, make a table of values. So what we're going to do when we're making a table, we're going to pick a number for H, and we're going to see what T that gives us. Now, it's very good. What we're always going to do when we want to graph something, since any 2 points are going to make a line, we always want to pick 3 points to make sure that we're doing it correctly. So we're going to pick 3 H's and see which T's that gives us. Let's pick our first H. Let's say H, hours, is 0. Let's say no time has passed. So if no hours have passed, so we have negative 11 plus 2H plus 2 times 0. That makes this 0. That gives us just a negative 11. Okay, let's say after 2 hours. Let's see what happens after 2 hours. So that's negative 11 plus 2H. Our H is 2. That's 4. 2 times 2 is 4, which we know. Negative 11 plus 4 gives us a negative 7. And let's see what happens after 4 hours. Okay, negative 11 plus 2H. Our H is 4. That makes this 8. Negative 11 plus 8 gives us a negative 3. Now we're going to take these, and these are actually our ordered pairs. This is 0, negative 11. That's what this point is. This point is 2, negative 7. And this is 4, negative 3. Let's go ahead and graph these. Let's graph 0, negative, well, first make a table. We made our table.
Okay, and now you've decided to put H as the first coordinate and T as the second coordinate, which is fine. So it's important when you graph that you label your axes accordingly.
Oh, thank you so much. So we're going to put our H here and our T here.
And what would be an appropriate thing to count by you don't have to count by the same amount on each axis, but you can.
Okay, well, it looks like since we have to see how big of a range we have. So we have to go all the way down to negative 11 over here. So it looks like we shouldn't really count by ones. Let's count by twos maybe.
Okay.
So this could be 2, 4, 6, 8. Here.
That would be ones.
Yes, there we go. We're going to do here 2, 4, 6. Hope you all can see this. 8, 10.
You don't have to number
12.
every space.
Okay, so we get the idea.
Just get us started.
Okay, so 0, negative 11. On our X, or on our H, we're going to start off at 0. And then what does this negative 11 tell us to do? Go down. So negative 2, negative 4, negative 6, negative 8, negative 10, negative 11. Okay, so this is 0, negative 11. Let's see, now we have 2, 7. On our X-axis, on our H, we have 2. And then we're going to go to negative 7. Negative 2, negative 4, negative 6, negative 7. Okay? And 4, here, label 2, negative 7. And 4, negative 3. Here's 4, and we're going to go negative 2, negative 3. 4, negative 3. And then we use our fancy ruler here to draw a line. And see how they all lined up? Wasn't that great?
That's always important.
And it's good to label our line.
Okay,
T equals negative, this is the name of our line. My name is Julia, and its name is T equals negative 11 plus 2H. That's its name.
And you also want to mark on the vertical axis the scale you use there, because there is no guarantee that you use the same scale on both axes.
Yes,
and you really only have to mark one unit. So you could mark, say, that is 2, and that would be good enough, because you have to be consistent with your units always.
Oh, okay.
All right, let's do 1 or 2 more lines that maybe don't come from a situation, but are just simple problems to graph. Did I snag your pen there? I'm so sorry.
No problem. Y equals 3x minus 2. Well, again, we're going to make our little chart here. First, we're going to figure out an x. Again, how many of these should we get? 3 of them. So we're going to do 3.
How do you decide which one to pick a value for? Should you pick a y, numbers for y, or numbers for x?
I'm so glad you asked that.
You're welcome.
What you have to be able to do is, remember, you're going to have to plug something in. So you always want to plug the thing in that's going to help you do it the easiest. The one that's by itself is not the one you pick. This is by itself. You don't pick that. You pick the one that you can plug into something and do something with it. So if I wanted to pick, let's say, and for a 3, sometimes it's good to pick, let's say, 0, a positive, and a negative. Okay? Especially if it's not a word problem. Here was a word problem. We couldn't have picked a negative here because this was hours and we don't have negative hours. But here there are no words involved, so we can pick anything we want. Let's start with a 0. 0 is always easy. 3 times 0, that makes this 0, and we're left with a negative 2. Well, that was easy to figure out. 0 is always an easy one. You just have to make sure it makes sense in the problem. Okay, now let's pick, let's say, positive 2. 3x, 3 times 2, that gives us 6. Minus 2 gives us 4. Okay, how exciting. And let's pick maybe a negative 2. Okay, 3 times a negative 2 is negative 6. Plus another negative 2 gives us negative 8. There's our chart. Now, let's go ahead. We understand these are our points. Okay, we just put, here we go. Here are our points. Let's go ahead and graph them. Oh, we should probably label here. Here's our x.
Good.
Here's our y. Okay, and I think we can just use these every one.
Okay,
so we can call this 1, 2, 3. Okay, and we'll go the other way. 1, 2, 3. Very good.
Okay.
0, comma, negative 2 is right down here. We'll label them in a second. 0, comma, well, I'll do it right now. 2, comma, 4, 2 on the x, and 1, 2, 3, 4. How exciting. And let's see if our other point matches up. Negative 2 and negative 1, 2, 3, 4, 5, 6, 7. What do you know? There it is. Negative 2, comma, negative 8. Use our straight edge. Yes, folks, isn't that exciting? It worked. It is straight. It's a line. Okay, don't we just love math? Isn't algebra great?
Now, a few other questions that you can solve by either looking at the rule, which is the equation, or at the graph is a point on the line.
Okay.
What that means is you can look and see, is the point on the line? Or what it means as far as the algebra goes, is the point a solution to the equation?
Okay, so let's take a look here. Let's find where negative 2, negative 4 is. Is it on there or is it not? Here's negative 2, negative 1, 2, 3, 4. Here it is. Does that look like it's on the line to you? I don't think so.
Plus, we had already used negative 2, and we found that when x was negative 2, y had to be negative 8. So couldn't be negative 4 and negative 8 at the same time.
Just wouldn't be possible.
Okay.
So our answer to number 1 is no. Let's go to question number 2. If 5 comma y is on this line, what's the value of y? Well, let's take a look. 5, this is our x, what our x would have to be. So let's see where x is 5. 1, 2, 3, 4, 5. So it's going to be 5 comma something. Let's see. Well, our line doesn't go that high.
So now let's use the equation.
Okay, so let's use the equation. That means we're going to plug in x as 5. Okay, so let's see what happens. 3 times 5 is what? 15. 15 minus 2 is 13. What do you know? So our answer is, what is the value of y? Y equals 13.
Okay, we're going to leave that other question for another time and move on to a few special kinds of lines. And these are lines that are either horizontal, and if you look at a horizontal, you might notice that y doesn't change, or might be vertical line, in which case x doesn't change. So let's see what those equations look like.
Okay, well first we have y equals 4. Now we're going to go back to picking points. Now let's see what happens. What is this rule telling me? Ms. Warmer was telling us an equation is a rule. This equation is telling me that y always has to be 4. It doesn't matter what I put for x. I could put 0. What does y have to be? 4. Thank you. I could pick 2. What does y have to be? 4. Oh, I could pick -2. What does y have to be? 4. 4. As Ms. Warmer was saying, there you go. The y never changed. The y is always 4. What kind of a line is going to look like that where y is always the same? Well, let's take a look. You're going to have 0, 4, 2, 4, -2, 4. We're always going to have 4 up here. It's a good idea to memorize that y is going to be a horizontal line.
Because the y is constant and y doesn't change.
There you go.
Little numerical axis label.
Oh,
like a
yes.
1 there.
Okay.
And we're set. That's good enough. We don't care about it.
Okay. So now let's take the same thing here. X equals 2. All right, so x is going to be 2. What could y be? I don't care. 0, 2, 7, 2, 1. Okay, very nice, very exciting. Okay, so now let's go ahead and graph this. Here, 2, 0, 2, 7, 2, 1, 2, anything. Okay, so your line is going to look like this. And it's very good to memorize that whenever you have an x equals, it's vertical. See when you have a little x? See that V in there? There you go. That's a V showing you vertical. When you see X, it's a vertical line, like boom. Okay, there's a vertical line.
So again, in vertical lines, X stays constant. Just look at it. X doesn't change. Y is going up and down, but X is staying the same. Likewise, in a horizontal line, Y stays constant.
That was pretty good.
Okay.
Oh.
Ooh, let's skip the inequality.
All right.
And let's see if we're given a few points, could we come up with the equations? We're only going to do very simple equations, so be a very good observer here.
Okay. Well, let's see. Write the equation which contains these 3 points. Well, right away, you got to notice something pretty wacky about this. Look here. -2, 3, -2, -1, -2, 1. What is that looking like? That's looking like no matter what, x is always -2.
What kind of line is that?
What did we say about that x in there?
I heard you say vertical. Very
It's
good.
a vertical line. Okay, and let's go ahead and do the next one. -3, 3, -2, 3, -2.2. I'm noticing something a little wacky over here. What's going on? My y is always 3. That is horizontal. Very good. We wrote the equations.
Okay, I think we can go back and do that inequality that we skipped.
All right.
Okay?
Yes.
Now, the only difference between this, we have to think 2-dimensionally, not 1-dimensionally. The only difference is we're going to have not just a line of points, but a whole slew of points.
Oh,
we're going to get to shade some stuff in.
Oh, wow. Well, whenever we have an equal, let's start first with the idea of what the equality is, and then we're going to go to the real problem. If we had x equals 2, what does that mean? X is always 2. 2. X is always 2. Where is x here? 2. So we could have, let's say, 2, 0, 2, 1. We said it's a vertical line.
Dot,
vertical.
dot, dot, dot.
Okay. Now, the reason why I'm dotting, does this thing say equals? No, it says greater than. Where are the x's greater than 2? Well, here's a 3, a 4, all of these. Hey, look at all of that. All of this is where x is going to be bigger than 2. Here's all the 3s, the 3.5s, the 4s. So we get the idea. This is the graph. Here's x greater than 2. Don't you have to put it dotted because it didn't have an equal sign in there.
Okay, so we hope you picked up on how to graph equations. See you next time.
Yeah.
Dotted. Good. I'll talk you through it. And we'll point out in both cases, we're moving the same distance for 5. 5's in the middle. Welcome to
this edition of
Math in Your Face, the J Squared Show. Hi, I'm Jane Wortman, head of the math department here at Beverly Hills High School.
And I'm Julia Bloom, the academic director of the Beverly Hills Tutoring Center.
And Julia and I are here today to help you with algebra. You remember that show. All right, we hope you use this program
to review things that you might have learned in class.
Or possibly to see things that you missed because you were absent from class.
Oh, we hope you weren't absent, but in any event, we want you to review along with us at home and remember something.
If you want to learn math at a better pace,
try putting some math
in your face. Julia, I think you're having too much fun here.
I think I am too.
All right, we're back in Chapter 7 of the algebra book, and we're going to be working on the middle 3 sections dealing with distance and a concept called absolute value, which is directly related to distance. Matter of fact, we talked about before that the absolute value of a number we thought about as its distance from 0. Now we're going to be looking at the absolute value of things not from 0 but from somewhere else. And we're going to be just counting along the number line. Again, thinking I can go left or right if I'm talking about absolute value. I just care how far, not which way. So let's look at our first example here.
Okay.
We're going to read that first expression as the distance between.
We're going to talk about this as the distance between some number and 5, or between 5 and some number. The distance between 5 and some number. 5 and we don't know what, some number, is, what is that distance between these two numbers? It is 3.
So if you draw a number line.
Okay, here's my number line. So the distance between 5 and some number, well, we have to start with 5. Between 5 and some number, what is that distance going to be? It's going to be 3. So now, as Ms. Wortman was telling us, it could be 3 on this side, or it could be 3 on this side.
And I want to be right at one of those 2 points, exactly 3 units away from 5.
Okay, so what is this 3 this way? That's 8. What is 3 this way? That's 2. So the distance between 5 and some number is 3.
Okay, what are the 2 numbers? Because that's what we're really looking for. What values of x make this true?
The 2 values would be then 8 and 2.
So either x equals 8 or x equals 2.
Or x equals 2. And if you actually were to substitute those in, you would see the absolute value of 8 minus 5 is 3. The absolute value of 2 minus 5, 2 minus 5 is a negative 3, and we learned that before, that ends up being 3 also.
The absolute value of negative 3 is 3, right. All right, we can do the same concept even if we have an inequality. We're thinking distance away from 4 this time.
Okay.
And what do we want to know about that distance away from 4?
So the distance between 4 and we're not sure what, and some number, it's not going to be equal to 1. It's going to be greater than 1. Well, if we take a look and we actually draw it out on a number line, as Ms. Wortman was showing us, so the distance between 4 and some number, well, we'll start with 4. The distance between 4 and some number on either side is going to be bigger than 1. Well, here's 1 on this side. That gives me a 5. Here's 1 on this side. That gives me a 3. But now let's take a look. Is the distance supposed to be 1? No, it's supposed to be the stuff that would be greater than 1. Not including. So all this stuff is a little bit more than 1 away, or maybe a lot more than 1 away. And all the stuff on this side is a little bit more than 1 away also. So here are our possibilities.
And we have inequalities for our solutions because we started with inequalities. And all we have to do is just look at the graph and describe what we see.
This is going, all our x's are going to be less than 3. Or they're going to be greater than 5.
Okay, and notice in both cases, the number that we were starting with in our absolute value is sort of in the middle of the two numbers that are important in our solution. The two important numbers here were 2 and 8. 5, the number we were counting away from, is right in between them because we were counting equal distances from 5. Here we're counting equal distances from 4. So 3 and 5 were our important numbers. 4 is right in the middle.
Okay, and that's going to really help us with other problems to remember that this number you see inside the absolute value is going to be right smack in the middle of something.
Okay, so in these two problems, we started with an absolute value expression and we created the graph to help us find the solution. The next problem is a little more involved because it requires us to go the other way. We're starting with the solution and we want to get back to the absolute value. And that's where that middle of the interval is so important.
Well, we have 3, 4, 5, 6, 7. Okay, this shows us that we want everything that's in between.
Draw the graph a little bit above the number line, then you can distinguish it. There we go.
Oh.
No,
Okay.
that's fine.
Okay.
Okay, we wanted everything between 3 and 7.
Okay.
So in the absolute value expression, the important number inside the absolute value expression was always the middle of the other numbers in our solution, the middle of the interval.
Here's
So
the middle.
what number do we have in there?
That's 5.
So that means we're measuring distance from 5. And how do we measure
Okay.
distance from 5? How do we express that?
We express that as x minus 5. Distance and difference between two things. When you're talking about between, you always do a subtraction problem.
Okay, so we want to be measuring distance from 5. And how far are 3 and 7 from 5?
Okay, our little endpoints here are 2 away on this side and 2 away on this side. So our distance from 5 is going to be 2. Now, is it less than 2 or is it more than 2? All these things. This point here, is that less than 2 away from 5? Sure is. Is this less than 2 away from? Yes, it is. It's less than, and not only that, it's less than or equal to because it also includes these points.
Okay, so again, a review. If you have those key numbers in your solution, when you create an absolute value expression, the number in the absolute value that you're subtracting from x is the middle of those two key numbers. And then you just look at the picture. Did you want to be close to that number or far away from that number?
And we want it to be close this time.
Okay, great. The next idea we're going to look at is as an old friend. If I know that 5 squared is 25, then I can take what's known as the square root of 25 and get back to 5.
Okay.
That symbol's called a radical. Now that doesn't mean we are like far out kind of people, but that is called a radical. Okay. And here's a cute bit of information. The number inside, that's called the radicand. Okay, so the square root of 25 means what squared makes 25.
Okay, so all that we have to do then is break apart 25.
We could even do that one without breaking it apart. We just know that one.
We just know that that's 5, that that's the square root of 5 squared, that this is just 5.
Okay, and it's important to know that this radical always implies positive square root. Positive square root. So you're going to say, well, how come the next answer is negative?
Well, the next answer would be negative because we have something in front of the square root sign. What is that? That's a negative sign. So our answer is going to have to be negative. Now, if you break apart 121 into these two things, that would be 11 times 11, 11 squared. So when you remove it from that root sign, you're going to get an 11, but what do we have in front? That negative sign. Your answer is a negative 11. Why is it negative? Because you had a negative in front of there.
Now, there's a really cool way to indicate you want both a positive answer and a negative answer. You know that one?
Hey, it's a pretty funky little sign there.
Okay, and we read that as plus or minus. It indicates two different answers. Plus or minus, we read it as two answers.
Different answers. And we're going to need to have two different answers. You understood what I meant. Okay.
All right.
We're going to need
now we're going to be solving equations that involve taking square roots.
Aha. And that's when we're going to have two answers.
Right.
You know what, everybody? When you have to solve this, how are you going to get rid of that x squared so that you end up with x equals the answer? You're going to have to get rid of that little squared thing. How? By square rooting it. So we're going to have to go like this. Like this. and like this. That's going to undo that squared sign, but
You didn't leave yourself room, did you?
yeah, no, we didn't. If you draw that square root sign in a problem, you also have to draw that fun little plus or minus sign. So, here's our little plus or minus sign. We'll redraw that. That's x squared equals, if you drew that, you also have to draw that.
And you only draw it on one side. You only put the plus or minus sign on one side of the equation, not both.
So then these two cancel each other out. That would give us x equals, we know that the square root of 81, that's 9 times 9. So our answer means we have two answers, is plus or minus 9.
You square 9, you get 81. You square negative 9, you get 81. Okay, what about x squared equals 0? Let's just get through these quickly.
Yeah, the same idea. The only funny thing about this, normally you put this in, but you normally have to put the plus or minus, but there's no such thing as plus or minus 0. And you can just understand 0 times 0 is 0. Very good.
Okay, this one, careful.
Okay.
Let's be observers. Wait a minute. You're not going to start taking square roots here, are you?
We are not, because I just thought it was a little crowded, but I just wanted everybody to be able to see. We're going to take the square root, but look what happened. Could we put a square root sign with something negative inside?
Well, forget even that. Could something squared even equal a negative number?
No, not in this math.
So no work involved. There are no solutions.
No solutions.
All
okay.
right. Now, the most famous illustration of using squares and square roots is the Pythagorean theorem.
Whoa!
Named for
Pythagoreans.
No. Okay, and what that tells us is if you're dealing with a right triangle, it only works for right triangles. The square of one leg plus the square of the other leg equals in length to the square of the hypotenuse, which is always the longest side. So we're going to look at a few illustrations as we close out today's problem. We'll get in as many as we can in the last few minutes of our show today, where we illustrate using the Pythagorean theorem.
Isn't that exciting? So c squared is always your longest side. That's the hypotenuse, and you just plug things in. So here our a is 5. 5 squared plus 12 squared equals, we don't know what c squared is, so we'll keep it as c squared. That means 25 plus 144 is c squared. 169 is c squared. We have to take the square root of each of these. And normally we'd have to do our plus or minus, but could a side ever be negative? This could not be a negative. So at this point, it is just 13. We figured out this is 13. C is 13. Very nice. Let's go ahead and do the same thing over here. A squared plus b squared. Always write your formula out first, then you can plug things in. Now be careful. Don't start just plugging in. You have a b. You don't even have an a. So don't plug in anything for a. A squared plus 10 squared equals 20 squared. Let's keep going. A squared plus 100 equals 400. We're going to subtract that from both sides. A squared equals 300. We are going to have to take the square root of both sides. Normally, we'd have to do plus or minus, but this is a side. It can't be negative. So we say A is the square root of 300.
Now, that's not one of our special perfect squares. We can't just pull that one out, can we?
No, we couldn't.
No.
Well, we could figure out it's in between two of them.
Okay, I happen to know, because I'm strange like this, that 17 squared is 289.
Okay.
And 18 squared is 324. So A has to be somewhere between 17 and 18.
So
and
we'll
at this
say-
point, you could use your calculator to approximate.
Okay, so we'll say A is approximately 17.
Okay, I think as we close out today, we can do our last example. Hope you learned something about the Pythagorean theorem and distance. Okay, and come in next time and we'll teach you how to simplify the square root of 300.
Oh, that is actually a fun thing to do. All right. These two cancel each other out.
Well,
This
cancel.
7, well, they undo each other or whatever.
There we go.
Plus 3 squared is 9.
Oh, this
equals
one came
C
out
squared.
nice.
16 equals c squared. We're going to have to take the square root of both sides. Normally,
stop
you'd have to
talking.
do the plus or minus, and c is 4. Bye, guys. Have fun skiing.
This will be after I've skied. Look, we got through everything, Julia.
I can't believe it. It's like the only time we've gone through everything, and it's the only I mean, you told me like.
Here. And I want to know this distance. Well, last program we looked at distances along horizontal lines. So let's create some horizontal and vertical segments, because the distance along verticals is just how much x changed.
Right.
And we'll just throw in these absolute values just to make sure.
You want me to put that on there?
That's actually. And welcome to
This edition of
Math in Your Face, the J Squared Show. Hi, I'm Jane Wortman, head of the math department here at Beverly Hills High School.
And I'm Julia Bloom, the academic director of the Beverly Hills Tutoring Center.
And Julia and I are here today to help you with
Algebra.
Got it. So we hope you use this program
To do a lot of different things, but mostly to review what you might have done in class since you showed up.
and possibly to review things that you missed because you weren't in class for one reason or another.
That's right. But even if you, for either of those reasons, we want everybody at home, moms, dads, siblings, follow along and do the problems as we do them here, and remember something.
If you want to learn math at a better pace,
Try putting some math
in your face. Great. We're closing out Chapter 7, which some of you may be working on first semester, some of you may wait till second semester. Doesn't matter. You need to learn this stuff.
That's right.
All right. In the last few sections, we're going to put together a few of the ideas that we've been working on up to now.
Okay.
Last program, we left off with taking square roots, finding square roots, simplifying square roots, and we were talking about perfect squares, like square root of 36. You know that's 6. But you could also think of 36 as 4 times 9. Well, 4 is a perfect square itself. Square root of 4 is 2. Square root of 9 is 3. Sure enough, 2 times 3 is 6. Got the same answer. So if you have a radical that you need to simplify, you can break it down into things that multiply, factors of that number, and then take the square roots of the individual factors.
Well, that's very helpful.
You want to do that to take as many perfect squares outside the radical as you can. Let's see it at work.
All right. Well, we're going to do exactly what Ms. Wortman said. Is 1200 a perfect square?
Nope.
I don't think so. So now let's try and find some perfect squares that we could just take out of there. Well, I know whenever I see 2 zeros, you can always do 100. And that's, even though there are other things we could pick, let's at least start with 100. This is 100 times 12. Well, now for sure, I can take out that 100.
We could even write that as the square root of 100 times the square root of 12.
Okay, times the square root of 12. And now I know the square root of 100 is just 10. Now I have 10 times the square root of 12. And we have to be careful. We can't just leave that as a square root of 12. Why? Because the square root of 12 is really, there's a perfect square in there that I could take out. So let's do this. Times, what is that perfect square that's in there? The square root of 4 times the square root of 3. Okay, see what we're doing? There. Now that square root of 4 we can pull out. So this is, going to give us 10 times, what's the square root of 4? 2 times the square root of 3. Let's go ahead and simplify. What's 10 times 2? 20 times the square root of 3.
Okay, and that's known as simplest radical form because there's absolutely no further simplifying you can do with the 3 inside the radical.
We're done.
Okay, so again, our goal is to always look for perfect square factors in the radical because we can simply take their square roots.
Okay, all right, well, let's take a look here. We're going to separate this, as Ms. Wortman taught us, the square root of 24 times the square root of a squared times the square root of b cubed. Well, the square root of 24, let's try and find something that's a perfect square in there.
Let's think. What 2 numbers multiply to 24?
Well, we could say 4 times 6.
Oh, is either of those a perfect square?
Well, 6 isn't, but 4 sure is.
That looks like a good choice
All
then.
right, 4 square root of 4 times the square root of 6.
Is a squared a perfect square?
Well, anything squared is a perfect square.
So we can just
Pull that out already.
We could, or we'll do that in the next step.
Okay.
Now, is b cubed a perfect square?
B cubed isn't, but there is something that is
What?
inside there. there's b squared in there.
Ooh.
This is b squared times b to the 1, or just b.
Okay, so now we're all set up to take out the square roots that we can and leave inside the radicals those things we could not simplify.
All right, so the square root of 4 we know is just 2.
Leave some
and
space.
There's nothing really that we can do with
What?
square root of 6.
So let's move that over for
Okay, we'll underline the ones that we're going to take out already.
Okay.
Okay, so now a squared we know is just a.
Okay.
Okay, the b square, square root of b squared is just b. And what did we have left? The square root of 6 and the square root of b. So we'll just times the square root of 6 times the square root of b. And let's rewrite this all nicely. 2ab square root, and we can put this back under 1 because there's nothing we can do with it, 6b.
Okay, one property that you do have to remember is that this rule about breaking up a radical and taking the square roots of the factors only works if all the factors are positive. Which means with numbers, we don't even concern ourselves, but if we have some variables in there, we must allow that the variables only represent positive numbers. Okay?
Okay.
That's just an aside, something to remember.
Okay.
All right, well, let's see this property at work. Oh, one place that we're going to use this property.
Yes.
We're going to go back to distance.
Ah.
Last time, we were measuring distance on a line. And we know that if you have a point over here on a number line and a point over here on a number line, and you want the distance, you just subtract. Make sure you get a positive answer, which means subtract big number minus small number, or else just take the absolute value.
Then you'll always get
difference.
a positive, happy kind of number.
Okay, we're going to take a look at distance not horizontal, not vertical, but diagonal. And we're going to put those three ideas together.
All
Okay.
right, well, let's go for it.
Give me 2 points that are not along a horizontal or vertical from each other.
Just draw them.
Just put a point. Let's call that one x1, y1
X1, Y1.
for the x and y of the first point.
Okay.
And another point, x2, y2. Very good.
Got a guess.
And what I am interested in is how far is it from x1, y1 to x2, y2?
So if you live here and I live here,
Yeah.
how far is it from your house to my house?
Right, straight line distance. Okay, and we're going to call that D for distance. Now, unfortunately, we don't have a grid pattern set up that way. Our streets only go vertically and horizontally. So we're going to plot out our horizontal then vertical path to get from point to point.
So instead of flying from here to here,
Right.
I'm going to walk down one big street
Right.
and then walk down the other one.
Okay, and notice that we have formed our old friend, the right triangle. And D represents the hypotenuse of the right triangle. And we know from last program, the Pythagorean theorem gives us a connection between the legs and the hypotenuse of the right triangle. Could you give me the ordered pair for this key corner point?
Okay.
It's along a horizontal line this way, and along a horizontal line, the y's stay the same.
Yeah, well, let's see. Well, how far over did I go?
Just give me
Here we go. Our x is going to be x2. Look
Right.
at that x point. I went as far over as I went there. And how far up and down did I go? Well, I went the same up and down as I did right here. So this is x2, comma, has the x's in common, and the y, 1. It has the same y as here.
We're on a horizontal line. We know all the y's are the same. Over here, we're on a vertical line. We know all the x's are the same. So now, can you tell me what this horizontal distance is?
Well, as you were telling us, whenever we want to find distance, you always need distance to be positive. Because even if I go backwards or forwards, it's still going to be, let's say, 5 miles, not a negative. So to make sure something is positive, you always put absolute value sign.
Then it doesn't matter which way you subtract.
That's right. So I'm going to be, remember, subtracting from here to here my x's. So I'll just put x1 minus x2. And as long as I put absolute value, then I know this is going to be positive.
Taking away space.
And here we go, and let's do absolute value here. Now I need to find out my y's, so I'll do the same thing. y1 minus y2, this absolute value sign means a positive number, and that's what I want.
Okay, and now we're going to create what's known as the distance formula. To get D, we're going to use the Pythagorean theorem.
That's what we want. So
So
what
we
is our
know-
Pythagorean theorem? A squared plus b squared equals c squared. And why don't we write this out a little bit differently? We could write this down as c squared is what? A squared plus b squared.
Okay, so now we know our C is D. C is D
Oh,
in our alphabet. So now we're going to write D squared
d squared.
equals,
What is our a squared?
that's x1 minus x2 squared. And
x1 minus x2 absolute value squared.
well, if you since we're squaring, we don't need to worry about the absolute value anymore. And our B is now,
Well, put it in there just no, write something consistently, but you do not need your absolute values anymore. So what is our formula to find out what this squared is, at least for, even though we're not going to want it
now,
squared?
yeah, we're going to now write our final formula, D equals.
Okay, so
D equals square root of,
D equals this. We're going to take the square root of the whole side.
Right.
The whole side over here. x1 minus x2 squared
plus,
plus y1 minus y2 squared. That is what D equals.
And the best way to think of this is just changing the x's, square it, changing the y's, square it, add them together, take the square root.
All right.
Find me some distances.
Okay. May I use the formula?
Think app, change an x squared, change an y squared, take the square root.
Okay. You want me to use the formula?
Sure.
Okay. Well, let's first, we always write off our formula at the beginning. D, our distance, is, remember, something squared plus something squared. And what are we going to be doing? Subtracting x's, subtracting y's. So we'll do x minus x, y minus y. Now let's start to plug in. Here's my x1, my y1. Here's my x2, my y2.
Does it matter which one you call x1 and y1?
It really doesn't matter. You can go either order as long as you're consistent. You can't flip-flop around.
Okay.
So what is our distance between these 2 points? Our distance is, okay. Remember, let's subtract our x's. We're going to do x minus x. So 3 minus, what is this?
Negative 2.
Negative 2
Squared.
squared plus, I'm going to be subtracting and then squaring. Yeah, we'll just go ahead and do the same. Negative 1 minus a 4. Negative 1 minus 4, and that's going to be squared. Let's keep simplifying. Isn't this fun? What is 3 minus a negative 2? That is a 5 squared plus, what is a negative 1 minus a 4? That's really plus a negative 4. That is negative 5 squared. Okay, we're rocking and rolling here. D equals, this 5 squared is 25 plus a negative 5 squared is also 25.
Let me give you a hint. Next line, write D equals,
Yes?
2 times 25. Square root of.
2 times 25.
If you got one of them and you got another one, you got 2 of them.
But
Why
I don't
did I
know-
do that? Because we're going to simplify our radical and we like it in factored form.
All right. Once you see you have a perfect square in there, don't let go of it so easily. This is going to stay the same. Remember, we were just doing this. Square root of 2 times, what's the square root of 25? 5. You got to write this out properly. This is going to be 5 square root of 2. Da-da-da-da.
Okay, distance formula at work. In the last minute or so, let's look at another concept called chunking, where we put a bunch of stuff together. All right? Where we simplify our arithmetic a little. I just was told that we missed 1 minute.
Okay.
We knew we had 2 minutes, now we have no minutes.
Okay, but we'll try and see what we can get done. Okay, so if 4x is negative 3, we're going to need 8x for the next problem. Don't bother solving and plugging it in. If you know what 4x is, so then 8x is going to be twice that. What is 8x going to be? You need it for here. 8x is a negative 6. This is twice, so this is twice. Okay, so now we're going to plug it in. 8x plus 5, that gives me negative 6 plus 5, which is a negative 1.
Keep your chunks together.
Chunking.